In this section, we're going to do Unit 2, Lesson 6, and that is writing an equation given a graph. And we're going to concentrate on three different types of graphs. We're going to concentrate on linear, which we've done earlier in this chapter. We're going to do quadratic, and we're going to do square root functions. The first thing you need to know is what form you need to write these equations into. So no matter what you're given, I always tell my students, put it in slope-intercept form, y equals mx plus b. And remember from earlier in the chapter, we learned that m is the slope and b is your y-intercept. But then if we have a graph where we don't know what b is, it crosses at a fraction point, we can use an ordered pair on the graph, a corner point on the graph, and plug in for x and y and find b. We can always find the slope as long as we have two corner points. And then if we plug one of those corner points in with that slope, we can always find b, which makes it nice. Now you need to understand that the parent function for a slope-intercept form or for a linear equation is y equals x. But when we're generating equations for lines that are linear, we are not really going to worry about the parent functions and the translations or the transformations on that graph. It's just a lot easier to understand slope-intercept form. You can get those equations very easily. The transformations become important when you're dealing with all the other types of functions, so like quadratic, cubic, logarithmic, exponential, square root functions. The parent function then and the translations, the dilations, they become more important when you're dealing with those type of equations. But linear, it's just easier to just learn slope-intercept form. A real quick review of linear equations. If I have the equation y equals x, if I take that equation and I try to isolate the slope and the y-intercept, basically y equals x is just the same thing as y equals 1x plus 0. And if we know the m, or the number in front of x, is our slope and the number added to that x is our y-intercept, we can see pretty simply that in the parent function, the y-intercept would be 0, so that means it crosses the y-axis. The slope is 1, so from that y-intercept, we can go up 1, right 1, because the slope, remember, is rise over run. So if the slope is 1, rise over run would be 1 over 1. So rise is 1, run 1. We go 1 over 1 every time to get to the next point. So there's a quick review of slope-intercept form. We will use that form to find the equation of any line that I give you. I've put three different lines on my graph, and we're going to find the slope-intercept form for each of these lines. I've got them color-coded so that you can see which one we're working with. I'm going to work with the blue line first. So if my linear function or my linear equation is y equals mx plus b, the first thing I'm going to do is find b, where it crosses the y-axis. So if you look at that blue line, it's crossing b at 1. So my y-intercept is 1. So I can just go ahead and put a plus 1 here. And then I'm going to find my slope. Well, in order to find slope, I need to find two corner points. So I know 1 is a corner point. And then I could go up right here is another corner point. I could choose any corner point on there. So I have this one, I've got this one, I've got this one. There are a bunch of corner points that I could use. I tend to try to pick two that are closest together so that hopefully I won't have to simplify my slope at all. So if I choose this one and this one, I'm going to count my slope. And my slope, remember, is rise over run. So I count up and then over. And in this case, if I start at the bottom point, I go up 1 and I go right 3. Both of those are a positive direction, up and right. Let's suppose I had picked this one and I went down to this point. Then my rise would be -1, and then I go left 3, so that would be -1 over -3. So it still gives me a positive 1/3 slope. So my slope here is 1/3, and I have y equals 1/3 x plus 1. Now we've already done this once in this chapter, so this shouldn't be new. This is just a review real quick of some stuff that you really should already be familiar with. Okay, next let's look at the green line. If you look at the green line, the first thing again that I'm going to do is I'm going to find the y-intercept. That is at -3. So If my formula is y equals mx plus b, my b will be minus 3. So I put that minus 3 in my equation. The next thing I need to look at is the slope. If I'm going to count that slope, look at the direction that the slope is going. I know that my slope is going to be negative for that line. So if I use 2 corner points, I'm going to use this one. And if I just travel up, it looks like that's a corner point. So my slope, again, is rise over run. So to go from the bottom point to the top point, I would go up 2, left 1. So that's a 2 over negative 1. 2 over negative 1 is negative 2. So my slope there is negative 2. I have to remember, I can't forget my x. And so it's y equals negative 2x minus 3 for that linear equation. Next, look at the red line there. That red line is a little bit different because if you notice, there is no way we can figure out what b is looking at that graph because b is somewhere between 5 and 6. And you have to be real careful that you're choosing corner points to plug in here. So I'm going to go ahead, I can't use my y-intercept as a corner point. So I'm just going to choose 2 other points kind of at random. So I'm going to choose that one, and I'm going to choose this one right here. Now, I can get the slope very easily by counting from the bottom corner point up. I go 1 and left 2. So that slope is negative 1/2. Okay, so I know for the red line, my slope is negative 1/2. And then the other thing I need to pull out of that line is one of the points. And it doesn't matter which one you use. As long as you use one of the corner points, it really doesn't matter at all which one you use. Okay? Now, I tend to pick one that has positive coordinates. I think that's easier to plug into my slope-intercept form. So I think I'm going to choose 1, 5. And you'll learn little tricks as you do math of what you think would make things come out a little bit easier or make the math a little bit easier, and that's always what I try to use. So the point 1, 5 is the ordered pair that I'm going to use, and by knowing a slope and an ordered pair, I can plug into either point slope form, or I could plug directly into the slope-intercept form and get my b value. So let's do that. I'm going to go ahead and plug into this because I think that's probably what most of you are used to. If I plug this information in, well, my x value is 1, my y value is 5, and my m value is negative 1/2. So y is 5, m is negative 1/2 times x, which is 1, plus b. And so then if I do my math here, I've got negative 1/2 plus b, and if I subtract or add the 1/2 over, I've got 5 and 1/2 for b, or 11/2. So y equals negative 1/2 x plus 5 1/2, or 11/2, would be my slope-intercept form for that equation. So again, you don't have to worry so much about parent functions with linear equations. It's just as easy, or actually it's easier, to just plug into slope-intercept form to find the equation of the lines. In this segment, we're going to talk about quadratic functions, and you need to understand that the parent function of a quadratic function is y equals x squared. Now, we went on to say, when we did quadratics in chapter 1, we talked about how to graph y equals x squared as the parent function. So I've got that over here. Here's the parent function. If we plug 0 in for x, we have 0, 0. 1 in for x gives us 1, 1. 2 in for x gives us 2, 4. 3 in for x gives us 3, 9. And then we talked about how symmetry in the parent function, or really in any quadratic equation, there is an axis of symmetry that goes vertically through your vertex of your quadratic function, and that quadratic function is symmetrical to the other side. So as long as we have one side of the quadratic function and the vertex, we can use symmetry to graph the other side, or we could plug negative values in. So -1 squared is 1, -2 squared is 4, and so on. So there are a couple of different ways you could find those things. But from this, we took out some very important information, and that's what I want to review with you first. First of all, we know that the vertex right here on our parent function is 0, 0. And so if we were to write this in vertex or graphing form, we said that the parent function would be y equals x minus 0 squared plus 0. Still mathematically the same exact equation, but we're accounting here for the vertex in our formula. Plus, we need to think about what number might be here. Well, in front of the x squared here is a 1, so my a value in graphing form would be a 1. But we need to understand what happens when this has been translated somewhere else, or what happens when this has been reflected across the x-axis. So that's the information that we need to consider when we're trying to use the parent function to come up with equations for other functions. We also had said that the number in front of the x squared term is your a value, and we said that if the a value is between 0 and 1 or 0 and -1, it makes the equation wider. And we said that if the a value is greater than 1 or less than -1, it makes the equation or the graph thinner, narrow, okay? So all of those things need to be considered when you're writing equations given a graph. And so that's what we're going to do in this section. Let's go in the same direction that we learned in chapter 1 first, to show you how graphing form relates to our parent function, and then we'll go in the opposite direction. So let's just suppose that I have the equation y equals, and I'll just keep a 1 times x plus 2 squared minus 5. When we were doing this in chapter 1, we said that the number that's inside tells us whether to move right or left, and it's opposite of what you would think. So this plus 2 is telling me to move left 2. And then we said the number on the outside is telling us whether to move up or down. And this is a minus 5, and the direction of our movement is going to be the same as what you would think. So a minus would tell us to go down. So every point on my parent function for this graph is going to go left 2, down 5. So my vertex will go left 2, down 5. This point will go left 2, down 5. This point will go left 2, down 5. And so on until we end up with a graph that is very similar to this in shape, but it's been translated left 2, down 5. Okay? So if I do this, there are a couple things I want you to notice. Okay, so here is my translated function, and it does keep going, but I'm just going to do that much of it. There are a couple things I want you to notice. Okay, in the parent function, from the vertex, if my a value is 1, only if the a value is 1, okay, this tells me to go right 1, up 1 to get to the next point. I go right 2, up 4 to get to the next point. So if it's a standard size parabola where you have not made it wider or more narrow, okay, if your parabola from the vertex to get to the next point goes right 1, up 1, and then right 2, up 4, you know your a value is 1, okay? Now, if you can't remember that, no big deal. You would have to plug into this equation to find a, okay? It would end up being 1 when you plug some information in. But if you recognize that from the ordered pair that is the vertex, you go right 1 up 1, and then right 2 up 4, and then left 1 up 1, left 2 up 4, and it's that same width, you know that it's just been translated. A has not been changed, so there is no dilation, meaning it doesn't get wider or more narrow, okay? If you recognize that right off the bat, the equation is very, very easy to come up with, okay? So what I'm going to do is I'm going to go backwards. I'm going to put another graph up here, and we're going to talk about, okay, is it the same width? Is it right 1 up 1, right 2 up 4 to get the width? If it is, I'm going to show you how to real quickly generate the equation for that. Now, if we say no, it has been widened or it has been more narrow, then we're going to have another process to do it. That process will work for all of them, but for the ones that have an a value of 1, it may be easier to do it this way. So here I have some more graphs. I still have the parent function here in black, but we're going to take these color-coded graphs and we're going to find the equation of those lines by noticing how this thing has been translated. And if you look at all of these, now remember the parent function from the vertex, we go right 1 up 1, right 2 up 4, and then we can use symmetry for the other. So what we need to check for first with all of these is it showing that same pattern from the vertex right 1 up 1, right 2 up 4? If it is, then it's a very simple parabola that has the a value of 1, okay? So let's look at this one. From the vertex, I go right 1 up 1, right 2 up 4, and then we've got symmetry for the other. So I know for that blue function, my a value is 1, okay? Well, if my a value is 1, then I know that my formula for the parent function is y equals 1 times x minus h squared plus k. Now remember, hk is the vertex of my parabola. So if I'm looking at this one, the vertex here is this ordered pair 6, 2. So my vertex is 6, 2. So I'm going to plug 6, 2 in for h and k to get my equation. So I've got y equals 1 times x minus 6 squared plus 2. That is the equation of my translated blue graph. For my green graph, if you look at that, it's going up. From the vertex, we went right 1 up 1, right 2 up 4, symmetry for the rest of it. So it again is a very simple equation that as long as we know our vertex, we can plug into the equation. My vertex here looks like -3, -7. My formula is y equals a times x minus h squared plus k. And we're going to plug that information in. So y equals, now I know a is 1 because remember we went right 1 up 1, right 2 up 4. That it's got the right pattern. It's not any wider or any narrower than what we started with in the parent function. We'll address those in a few minutes. All right, so here, h in this one is -3. So I'm going to plug in x minus -3 squared plus k. Well, k is -7. So that's plus -7 or minus 7. And then right here, if we have minus a negative, well, we know minus a negative should be a plus. So that is my equation for the green function. So now look at the red function. What's different about the red function? First of all, we're not going right 1 up 1. We went right 1 down 1. We went right 2 down 4. So the ratio of the points are the same, 1, 1, 2, 4, 3, 9. But instead of going up, we're going down. So this thing has been flipped across that x-axis and translated from the original vertex, okay? The way we go about this one is the same. Since we know the ratios are 1, 1, 2, 4, but it's upside down, we know a is 1, but it's not +1, it's -1 because it's upside down. We learned in chapter 1 that if the parabola is upside down, then your a value is negative, okay? So we know a is -1. So we know the number in front of the parentheses has to be -1. So my vertex here, I'm going to look at that. That is 4, -3. So to write the equation for that one, I have y equals, remember a is here, x minus h squared plus k. Now, we talked about a. We know it's a form of 1, but since it's going down, it has to be -1. So a is -1, so I've got y equals negative, and we could put a 1 there, or just a negative is fine. X minus h was 4, so that's x minus 4 squared. And then k is -3, so that's a -3. So there's my equation for the red graph, okay? But what happens if my ratio isn't right? What if it doesn't go right 1 up 1, right 2 up 4, right 3 up 9? What if my function is wider or more narrow? Well, it's not much more difficult than this. As long as you can find the vertex and one other ordered pair, you're going to be able to find the equation very easily by using this formula right here. So this is a formula you're going to need to commit to memory. Y equals a times x minus h squared plus k. That is vertex form of a parabola. And honestly, we use that form so much in Algebra 2. There's so much we can do with that form. Memorizing it will make your life easier, believe it or not. So it would be good if you go ahead and get that memorized so that as we refer to it later with completing the square and writing things in standard form, it's going to be a lot easier if you go ahead and know that. So as we stated before, the graphing form of a quadratic equation is y equals a times x minus h squared plus k. Make sure your x minus h is in parentheses. And remember, the vertex of this function is the ordered pair hk, okay? So the vertex, if we know the vertex is hk, then we could pull that vertex from any quadratic graph that we have and know what to plug in for h and k. And then in order to find a, really all we have to do is kind of do what we were doing with slope-intercept form. We pick an ordered pair that is on the graph and plug that ordered pair in for x and y, and that will leave us with the only variable being a, and we'll be able to figure out what a is and then plug it back in to the graphing formula. I'm going to do the blue function first. So if you look at that blue function, the vertex of that function is -5, -2. So my hk is -5, -2. So I'm going to go ahead and plug those numbers in for h and k. So I've got y equals a times x minus h. Well, minus -5 would be a plus 5 squared, and then k is -2. So I've plugged the vertex into my formula. Now I have three variables, y, a, and x. Well, I could eliminate x and y by picking any ordered pair on that graph other than the vertex. Remember, the vertex has already been plugged in for hk, so we can't plug that in again. That wouldn't help us, so we need to pick a different point. So there are several points here. I think I'm just going to pick this one right here. That's -1, 6. So another point on that is -1, 6. So I'm going to take -1, that's going to be my x, 6 will be my y, and I'm going to plug into this equation. So y is 6. I don't know what a is. X is -1. And in solving that, I will be able to figure out what a is. So if I do the math, I could add the 2 over, that gives me 8. -1 plus 5 is 4. So that's 4 squared. 4 squared is 16. I'm going to rewrite that as 16a. Then I divide by 16. So 8 divided by 16 is 1/2. So that tells me that a is 1/2. So the equation for the blue function there is y equals a was 1/2 times x plus 5 squared minus 2. We've found the equation for that quadratic graph. Look at the green graph next. That one's very similar. We know in that case, my A has to be negative because it's facing down. My vertex is still HK. So my vertex here would be 2, 4. I'm still going to use the formula y equals A times x minus h squared plus k. So if I plug the vertex 2, 4 in, I have y equals A times x minus 2 squared plus 4. And then in order to find A, I would pick any other point on my graph. So I'll just use this one right here. That point is 4, 2. So if I plug 4, 2 in for x and y, I would have 2 equals A times 4 minus 2 squared plus 4. 4 minus 2 is 2, and 2 squared is 4. So that leaves me with 2 equals 4A plus 4. I'll subtract the 4 over, divide by 4, and I'll have negative 1/2 for my A value. So my equation for that quadratic is y equals negative 1/2 times x minus 2 squared plus 4. So if you know the graphing formula for a quadratic, it's that simple. You plug in a point and the vertex and you'll be able to solve for A to come up with your quadratic equation. Here's another quadratic equation. The vertex is at -1, -5. This one looks a little more narrow. We know A is going to be positive because it is going up. We know graphing form of the equation is y equals A times x minus h squared plus k. So see if you can take the information off of that graph, plug it into the formula to come up with the quadratic equation for that function. So looking at that function, my vertex was -1, -5. That's my h and my k. You may have chosen a different point, and that's okay. Whatever point you choose, you should still get the same A value. You should get the same final answer. That doesn't matter. So it might be good if you choose a different point than I do. I'll go ahead, I'll use this point right here, -3, 3, as my xy value. So, if this is my xy value, x is -3, y is 3. If this is my vertex, h is -1 and k is -5. So I'm just going to plug them all in at once. So y was 3. We don't know what a is. X is -3 minus -1, so that'll be a +1, and then minus 5 for your k value. If I do the math, I can add the 5 over. -3 plus 1 is -2 squared is 4. So that's a 4a. If I divide by 4, a is 2. Now that I know a and I know my h and k, I can write the equation. There's the quadratic function for that graph. The next function that we're going to talk about is the square root function. And the square root function, parent function, is y equals the square root of x. And I have that graphed here in black. Basically, with the square root function, it's going to start at 0, 0. Your next point would go right 1 up 1. The following point would go right 4 up 2. The next point would go right 9 up 3. We're taking the square numbers and their square roots to form the graph. And we talked about these in chapter 1. We also talked about what would happen if we put a negative in front of that. If we have y equals negative square root of x, we said that that would reflect that black graph across the x-axis. So my starting point would still be 0, 0, but then we would go right 1 down 1, right 4 down 2, right 9 down 3, and get the reflection of that graph below. Okay, so that's what happens when we have a negative in front. Now, we also talked about what would happen if we put something, or if we change where the starting point of that function is. So a negative in front is going to reflect it across the x-axis. Now, let's talk about what happens if we put something on the inside of the square root and on the outside of the square root. We had said before that anything on the inside is going to make us go right or left, opposite of what the sign says. And anything on the outside tells us to go up or down from our starting point. And then we did talk about what happens if the number in front, if it's a fraction or if it's a whole number, and how it would affect the way the graph looks. So this is very similar to quadratics, but now we're dealing with square roots. So if I have something like y equals the square root of x plus 3 on the inside, and then minus 2 on the outside, basically what that does is it takes this entire graph and it moves each point on that graph left 3, down 2. So my new graph would be, there would be my starting point. Here would be the next point. That would be my new graph. Everything has moved left 3, down 2 for my new graph. So what we're going to do in this section is we're going to go in the opposite direction. I'm going to give you the graph and you're going to come up with the equation. Okay, in chapter 1, we were given the equation and had to get the graph. Now we're going to go backwards. So the parent function of a square root is y equals the square root of x. And we said that if there's a negative in front, it will reflect it across the x-axis. I still have the parent square root function here. And what we can do is we need to look at it. This one right here, we know that it is not a reflection. It's not upside down. So we know that the A is positive there. But sometimes students have a hard time deciding whether that thing has been dilated, whether it's wider or more narrow. So I'm going to show you how to do this so that you don't have to worry about that. I'm going to take some information that I learned in the quadratics, and we're going to kind of come up with our own kind of formula for a square root function. And basically we know that we don't know what A is, or the number in front. Okay, the number in front determines how wide or narrow that new graph is going to be. We don't know what that is. In the parent function, it's understood to be a 1. Okay, we know that whatever's on the inside, it's the opposite of what we would think, as far as whether to move right or left. And then what's on the outside is the same direction as what we would think. So we can kind of treat this like we treat the quadratic functions, in that we have an h and k. Now, in a quadratic, h and k is our vertex. Here, I'm going to call h and k my starting point. So if a is 1 and my starting point is 0, 0, my parent function would be y equals square root of x. But what if I don't have a starting point at 0, 0? Well, we can plug those numbers in for h and k, and then we can pick another point on the graph and figure out what a is by doing a little bit of math. So that's what we're going to do here. So my starting point here, it's not really a vertex, but it's going to be my h and k value. That starting point is -5, 4. So I'm going to go ahead and plug that in. Y equals a times x plus 5, and it's the square root of that, plus 4. So I plug that number in. Now I need to figure out what a is. In order to do that, all I have to do is pick any other ordered pair, a corner point on that graph, and plug it in for x and y. I'm going to go ahead and use this one right here. That's -4, 5. So I'm going to plug negative 4, 5 in for x and y. So y is 5. I've got negative 4 plus 5 inside. So if I do the math, negative 4 plus 5 is 1. Square root of 1 is 1. I can subtract the 4 over. So in this case, a is 1. So that means the equation of that line is y equals the square root of x plus 5 plus 4. Okay? So it's pretty simple when a ends up being 1. But a is not always going to end up being 1. So that takes us to the green graph there. Let's do that one next. Okay, so if we're going to do the green graph, my HK value is the starting point. So that is at negative 2, negative 5. So that's what I would plug in for my HK. So H is negative 2, so that'll be a plus 2 because it's minus negative 2. And then the minus 5 goes on the outside. And then I can pick any other point on that graph. I'll just pick this one this time. That's at 2, negative 7. So 2, negative 7. 2 would be the x value, and negative 7 would be the y value. So negative 7 equals a times 2 plus 2, and that's underneath the square root, minus 5. Well, 2 plus 2 is 4. Square root of 4 is 2. So that's 2a minus 5. I add the 5 over. So a will be negative 1. So the equation for that line is y equals negative 1 times the square root of x plus 2 minus 5. So if you know basically what the parent function is for your square root, and you know that h and k, h is on the inside, k is on the outside, the inside number gets a minus h, the outside gets a plus k, and then you know that the a value is in front of that, then all you need is your starting point and another ordered pair, and you can find the entire equation for that square root function. Remember, we're going to use the parent function of a square root function to determine what's happening for our other functions here. So we're just going to do the blue function together. Now looking at that, it looks to me like it's narrower than the parent function was. So it looks to me that there's going to be an a value, something other than 1 or negative 1. Okay? And then it looks like it's been reflected across the x-axis. In other words, it's upside down. So that tells me that my a is probably going to be negative. So when I'm thinking about doing the parent function for this and thinking about my starting point, I'm going to use the knowledge that I talked about when I taught you quadratics, okay? In a quadratic, we said h and k was the vertex. In a square root, we're going to let h and k represent the starting point of our function. So for this graph right here, the starting point is going to be at negative 6, negative 2. So my h and k is going to be negative 6, negative 2. And then I'm going to pick for my x and y another point on my function. So here, that other point on my function is negative 2, negative 3. Just be very careful, make sure you're labeling those points correctly. Otherwise, you'll get something that is probably not going to work. And then when I do my parent function, I know that in front of the square root, that's what we're going to call our a value. And then inside, I have my x minus h. And then on the outside, I have my plus k. Now, h and k always represent your starting point. Your other point on the square root function is going to be your x and y. Be very careful that you don't get those mixed up. HK has to be your starting point. So don't try to use negative 6, negative 2 as x and y. That will mess up the function. It won't work. Okay? So let's go ahead and plug in. Now y is the y value of that ordered pair on the graph. So negative 3 equals, we don't know what a is. I do know it's going to be negative because of the direction, but that's all I know about a. So I'm going to leave that blank. The negative should come through in the math. My x value is the x value on the ordered pair that we chose, so that's -2. My h value here is -6, so it's minus -6, which would be a +6. And then my k value is the k there, which is -2. And then at this point, I just do the math. I could add the 2 over, so that gives me -1. I don't know what a is, but inside there I have -2 plus 6, which is 4. Square root of 4 is 2. Then if I divide by 2, I have -1/2 equals a. So my a value is -1/2. It's negative, which is what we thought, and we knew it was going to be something other than 1. So my equation is y equals -1/2 times the square root of x plus 6 minus 2. So that's how you tackle square root functions. So now, I've got a red function up here. The starting point is at -3, 4. Another point on that line is at -2, 6. So this would be your HK. This would be your XY. See if you can plug in to this parent function and get the final answer. Okay, let's go through it together. Here, my starting point was at -3, 4. Another point on the graph was at -2, 6. So this will be my HK, this will be my XY. So if I plug in, Y is 6 equals, we don't know what A is. X is -2. It would be minus -3, so +3. And then my K value is +4. If I do the math, I can subtract the 4 over. -2 plus 3 is 1. Square root of 1 is 1. If we divide by 1, we get 2. So my A value is 2. If I plug in, my final equation is y equals 2 times the square root of x plus 3 plus 4. So that's the quadratic, no,